Are we all there?
Yes.
Yes.
No, I think Pooja is not here.
Pooja is not here. Let's wait a few more minutes. Okay. Is Pooja in? No, no, no. Do you have a way to check if she's around? Okay. I think we should start.
I sent her an email, so.
Okay, 2 more minutes and then we start.
I have a question about the lecture of yesterday. Can I ask now?
Sure. The question about what?
Lecture of yesterday.
Yes, please.
Yeah. Yesterday we chose that the state which corresponds to the maximum GZ is an eigenstate of G squared, right?
It must be.
Yeah, it must. Why it must be?
Yeah, we are constructing multiplets of J square and JZ.
Yeah. Why just the state which corresponds to the maximum GZ is always an eigenstate of G squared?
Because it's impossible. I mean, if you have selected the maximum JZ, and is a single state that has that maximum JZ obtained by maximizing the two LZ and SZ, right? Now, if there is a single state, it must be an eigenstate of J square almost by definition, okay? There's no other possibility. If there was an eigenstate of J square of larger J, it would correspond also to some corresponding JZ. So if you think a little bit, you realize that the fact that there is a single maximum JZ essentially brings directly to the conclusion that that must be the top multiplet, the top state in the multiplet of the corresponding J.
What do you mean by single maximum?
Huh?
What do you mean by single maximum of JZ?
There is a single state where JZ was equal to 3/2 in the story we said.
Oh, okay.
No other state had JZ equal to 3/2. Okay.
But
So what could
to...
be? I mean, it must be an eigenvalue of an eigenstate of J square as well, with eigenvalue J equal to 3/2. No way out. And you can verify. I mean, you apply J plus.
Yeah.
You get 0 and all these kind of things. All these tests tell you that.
Even in the case of L equal to 2, it's true. It's always true.
It is for L equal to 2 and spin 1/2. It is 2 plus 1/2, so it's 5/2.
Yes.
There is no way out. If you try to apply J plus to any other state, okay, you wouldn't conclude that it's 0, okay, because you get combination of. So this is the only state is unique. There is only one. And if you apply J plus, you get 0. So it must be the top state of the corresponding multiplet. That's it. Okay?
Okay.
Okay, good. So I think we start because I have seen now the number of participants is 12. So perhaps Pooja is in. Yes.
Yeah,
great. Hello, Pooja. Great. Okay, so today we'll be discussing about symmetries, and in particular symmetries in quantum mechanics. What is the role that they have in quantum mechanics? Okay, so symmetries are, I mean, very widespread concepts in physics. So let me start from describing to you something that you have learned presumably in linear algebra or some closely related subject. So I will discuss of space transformation. Okay. By space transformation, I mean people call it different name, isomorphism of space or whatever. Okay. I will to be more concrete, I will discuss the case of translations. So translations. And in the case of rotations, okay? You know both very well, but let me just quickly remind to you what they are, okay? Let me start from translations. Now, if I take a point in, say, in three-dimensional space, I call it X, okay? And I apply a translation by some vector A, so I choose a vector A, okay? The translation, the operation of translating the vector X by the vector X, by the vector A, is simply a new vector, X prime, which is X plus A, okay? Is it clear? Good. So given a vector, okay, X, I get a new vector X prime by translating by A. Fantastic. Very good. Now, rotations. Here, illustration is slightly more complicated, but not very difficult. So suppose that I have, let me draw a plane here, okay? Okay, I rotate on this XY plane. I have some vector, X. Sorry for the, I mean, X and Y are the label of the axis. X is now the vector of component X and component Y and possibly component Z. But I mean, if it is clear to you, I would leave the same symbol. Okay, good. How do I rotate, for instance, around the Z-axis? Remember, the Z-axis is an axis coming out of this page towards you? Well, I just rotate by an angle theta, for instance. Okay. And I obtain some new vector x prime, right? Now you know, presumably by linear algebra, that this also can be represented by a transformation. The transformation this time is parameterized by, say, theta and the axis z, which I do the rotation of. So, okay, so I call the transformation a rotation by theta and z, okay? Or simply theta and z, whatever, if it is clear. So let me just draw it better, maybe. I just use the notation, the transformation of theta and z of x is equal to x prime, okay? Do you know how to express x prime? Presumably, yes. X prime is equal to a rotation matrix, okay, applied to the vector x, y, and z, which is the coordinates of my vector x, right? How is the rotation matrix look like in the case I gave you above? Cos theta minus sine theta, cos theta for the x and y parts, and then there is 0, 0, 0, 0, and 1 for the z part. Okay, if you rotate around z, the z component doesn't change at all, and the x and y component, as you know very well, are changed by this cosine and sine thing. Okay, is it clear? Now, as you know very well, these are orthogonal matrices. Okay, which means that the transpose is equal to the inverse, okay, which is a nice way of calculating the inverse, because you just need to flip the off diagonal, okay. One thing that you also notice is for this rotation is that the determinant of r is equal to +1, okay. Cos square plus sine square, in particular, in this case, is equal to 1. And that's true for all proper rotation matrices. But there is also another important transformation, which is called the inversion. Okay. The inversion is rather simple, in fact, very, very elementary. If I have space, okay, and if I have a vector x, the inversion is simply the vector minus x, okay? So how do you represent it? The transformation associated to inversion of x is equal to minus x, right? And is equal to a matrix with -1 in the diagonal, okay? Is it clear? Very, very simple, okay? Apply to x, y, and z. What is the determinant of this matrix that I might call whatever, I? The determinant of I is equal to -1, okay? Notice product of 3 minus 1. In 2 dimension, by the way, it would be difference, okay? In 2D, I would have a determinant +1, but notice that if you work purely on the plane, and I have some vector x, and I give you -x, then that's totally equivalent to a rotation by pi. Okay? So in 2D, in fact, inversion is totally identical to a rotation by pi around the axis out of the plane. Okay? So what I told you here is in fact restricted to 3D. Very good. Now, putting together rotations and inversion, I can form what are called improper rotations, okay? Improper rotations are simply...
I have a question, Professor.
Yes, please.
I think that we have the inversion also depends on the plan of inversion. I mean, which plan that we inverse our vector through?
No. Inversion around the point, around the origin, not around a plane. Sorry. Maybe I should
Yeah.
specify. Inversion in 3D around the origin. The origin. Do not confuse this with the reflection on a plane. So I'll draw it here. If I have a plane, okay, I can reflect the point on the plane. Okay, that's a different object. I will not consider it reflection by a plane. Okay, this is not what I'm considering. It is an inversion with respect to the origin. Okay, so every point, okay, I can go. Every point is reflected around the origin.
Yeah.
Okay, is it clear? Clear? The difference between inversion around the origin and reflection by a plane. They are two different transformations.
Yes.
Okay.
Yeah, Professor.
Yeah, please.
Yeah, I missed your point here, inversion in 2D.
No, tell me again. I didn't understand your sentence.
I mean, you have done inversion in 3D, then I did not get the point in 2D. I missed the point about that.
Oh, the point is simply the following. If I am strictly in 2D, I take a vector x equal to, say, x and y, and I send it to minus x, so minus x and minus y. That's exactly, you see, first of all, that the matrix I representing it is -1, -1, right? It has determinant +1, okay? So the point is that the determinant of I is equal to +1. And you can verify that it coincides with this matrix, with this piece of matrix, when you put theta equal to pi, okay? Cosine of pi becomes -1 and sine of theta is equal to 1, okay? So in 2D, there is no real distinction between an inversion through the origin and a rotation by pi. That's the only thing that I was alluding at. Is it clear? Okay, so this is
Yes, fine.
special of 2D. Okay, good. Now, let's consider again, let's continue our discussion about rotation and inversion. You can put together a rotation followed by an inversion or the opposite and construct improper rotation. So an improper rotation are, say, whatever. I don't know, maybe I can, R is just R proper, so a proper rotation, followed or preceded by an inversion. Okay, you can do both. Okay. Since the product of the determinant, okay, you notice immediately that the determinant of R is equal to the product of the determinant of the proper rotation times the determinant of the inversion. This is +1. This is -1. So you see, if I have an improper rotation, the determinant is -1, right? But apart from that, so apart from the fact that you can essentially add some inversion into the transformation, you know what I mean when I say a rotation. Okay, good. Can I put together translation? Oh, sorry. Translations and translations plus rotations? Yes, of course. They are called Roto Translations. Okay? Roto Translation. Simply means translation. It simply means that you do both. Okay? So a transformation associated to some rotation R and some translation by the vector A acts on the point X by giving you a new point X prime, which is equal to the rotation of the point X plus the translation A. Okay? And these objects form a group. Form a group, which means that you can actually multiply two of those transformations in a rather kind of obvious way. So for instance, the transformation with the rotation R2 and translation by the vector A2, which is following a previous transformation by a rotation R1 with a translation A1, is totally equivalent to a single transformation where you rotate by R2, R1, okay? And you translate by, that's the only surprising thing, R2, A2, sorry, A2, A1, sorry. Plus A2, okay? Try to verify this rule of composition by just using this description of the Roto translation, okay? So you can very easily, yeah, the only tricky thing is this.
What is R2 times A1? What does it mean?
What?
What does it mean, this one? R2 times A1.
It's very simple. You have to try. Do you want me to try? I can try, but it's not the same thing, okay? Apply the first, okay? So I apply the first to a value to X, which means that I get R1X plus A1, okay? Then I have to apply the second transformation, which means that I have to apply R2 to the vector plus the second translation, okay? And the result of this combination of two objects is equal to R2, R1, X plus R2, A1 plus A2. And as you see, this is the combined rotation that I do to the vector X. And this is the combined translation that I do, which is R2I1 plus A2, okay? So that's the thing that I was asking you to verify. But since you asked,
So,
okay, the exercise is gone. You cannot practice. Pardon me?
A1 and A2 are vectors.
Vectors, always vectors. If A for me will be always a vector of some translation. Okay?
Yeah, okay.
Okay, so here. And this is a rotation. Okay? Very good. Now, this is just space transformation of linear algebra that we are particularly interested on. Now, I will discuss with you how this space transformation act on functions. After all, you know that quantum mechanics is about wave functions to start with, right? So I would like to know what happens if I do a space transformation to the wave functions of the Hilbert space. Okay, so let's do a simple example. Suppose that I have example is essentially the translation in one dimension. Okay, so I have some function. I draw it here. Okay, okay, this is x and this is psi of x. What does it mean, okay, that I'm translating the function by some value a? Okay, it means that I am getting a new function. Let's see if I can draw it different color. Okay, see if I can. So every point is translated by a. Something like this. Is it clear? Okay, so every point, maybe it's not particularly nice here. Okay. This point, or sorry, corresponds to this point. This point corresponds to this point, and so on and so forth. Okay, so all these objects are A. Okay, this is a new function. Let me call it psi prime of x. Is it clear? Is it clear or not so far?
Yes.
Okay. Now I want to know what is the function psi prime of x. Notice it's not a derivative. Psi prime stands for a new function. Psi prime of x. Can you tell me the relationship with psi?
No, psi x plus a.
Well, it is x minus a. The
Yeah.
function at this point, say here, x is equal to the value that the function had at the point that translated back, which is minus a, right? Okay, so that is the crucial relationship between the functions. So I can say, okay, let me define now. Notice, I define an operator P associated to this translation TA, and now acting, notice, the operator acts on the function, okay, on the function psi of x, and gives me what? Gives me a new function, which is this psi prime of x. The function is equal to the old function I had at point x minus a, okay? By the way, this is nothing but the function at the point which was translated back. So it's t to the minus 1 of a of x. Is it clear? X minus a, in other words, can be seen as a point x, which is translated back. So you see the minus 1 by a. Okay? If you translate forward the function, okay, the corresponding point that you have to take in the old function is the translated back point. Okay, you see it very clearly from the figure, right? You see this?
Yes.
X minus a. Very good. This is my new definition then. Okay, I define somehow an operator acting on the function corresponding to the space transformation. You see that this is a space transformation. It's a transformation of point. Okay, and now I am defining an object that works on the functions. Okay, takes a function and gives me a new function. Okay, let's use this general thing to make the story pretty general. Okay, so in general, my new definition is the following: if I have some space transformation T, whatever, that sends, so T associated to some rotation.
Sorry,
some,
sorry for interruption, but why you denoted T A minus 1?
Because remember, TA of X would be X plus A.
Yeah.
Okay, in order to have, you want the inverse transformation, TA to the minus 1, okay,
X
is a
minus
transformation that sends X into X minus A.
Yeah.
Okay, also you can rewrite it as T, in this case, as T of minus A, obviously.
Yeah.
Okay, if you want. But I prefer to write it as the inverse transformation. Okay,
Yeah.
so the minus 1 that you have there, okay, is you, I mean, you translate back. The same story, although more difficult to picture, by the way, holds true if I do a rotation. Okay, suppose that I take a function. Okay, let me just draw a two-dimensional function. Okay, so this is my function of two coordinates x and y. I do have some function, hard to draw, and I rotate around the x and y axis by some angle theta. Then obviously the new function associated to the rotation, okay, is equal to the old function psi at the point which was rotated back. Okay, is it clear? Same story, absolutely same story, simply more difficult to picture. Okay, this will be my general definition. So in general, I will say that a transformation T, given any transformation T that sends T x into x prime, which is some Rx plus A, whatever, Roto translation, then the P, the operator P, okay, acting on the functions psi of x, okay, associated to this transformation T is simply equal to a new function psi prime of x, which is equal to the old function at the point that is transformed back. Okay, so this is my general definition of how the transformations act on the function. Is it clear? Okay, good. These operators seem strange, but they are not. Okay, let's consider again the translation. Okay, look at this object here. I would like to show you that P of the translation A is in fact equal to e to the minus I A, the momentum operator over h bar. Okay, let's verify. I told you that PT is defined in this way. Okay, so PTA of psi of x is equal to psi of x minus a, right? Let's expand. Okay, let's Taylor expand. Assuming that the function has all derivatives that you want. Okay.
Sorry, Professor.
All right, please.
The PTA here is the transformation, or it is the operator?
Is the
PT.
operator acting on the function. This is function, okay? TA is the transformation in space that in this case does nothing. I mean, it does a very simple thing, the translation, okay? So this object here is TA to the -1 of x, okay?
Okay.
It's the example I gave a while ago, this one, same example, okay? Which I have then generalized in the yellow page here. But now I'm returning to the simple example, okay? So I want to show to you that this operator is in fact a simple operator that we already know very well, okay? Let me Taylor expand. If I Taylor expand, this is psi of x minus a, the derivative of psi of x, calculated at position x, plus minus a square over 2 factorial. The second derivative, let me indicate the second derivative. No, I don't like it because it makes very, I mean, it is confusing. So it's the second derivative plus all other terms, right? Okay, very good. Now, notice that I can write this object here, okay, as minus I, A, the momentum operator over h bar, applied to the function psi. Do you see why? Let's see. Minus I, A over h bar. The momentum operator is minus I, h bar, the derivative, right? Applied to psi. And you see immediately that minus I times minus I gives me this minus sign, okay? And then I have h bar and h bar that cancel, and I get exactly the result I wanted. In a similar way, you can prove that this object is nothing but 1 over 2 factorial, the application of this operator twice. Okay, because it's a second derivative. You iterate the first derivative and you get the second derivative. And this is true for all terms, okay? So in fact, this object is equal to 1 plus the operator minus AP over h bar plus its square plus all powers applied to the function psi of x, okay? And at that point, it's immediate to conclude that this is in fact the exponential of this operator, okay? Applied to the function psi of x. Is it clear? Okay? So you see immediately that indeed the object that I have here applied to psi is this, okay? So the translation operator, when you apply to a function, is simply represented by the exponential of momentum. It's a very interesting result. And by the way, it is a bit reminiscent of the following fact. You remember that if I have a state at time 0 and I want to obtain the state at time t, all I need to do is to apply e to the minus I h t over h bar to the state at time 0. Remember, this is the evolution operator. Okay? So the evolution operator is like something translating in time. So from 0 to t, okay? And this is, on the contrary, is a translation in space. Okay, so the exponential of momentum is a translation in space. The exponential of the Hamiltonian is a translation in time. Okay, so this is just a very, there is a difference. However, time is not a variable in quantum mechanics, is a parameter, while x is an operator. So there is a difference, but otherwise there is some strong similarity. Now let's move to the interesting case of rotations. Okay, now I want to prove to you, just to give you the final result, is the following. If I have the operator associated to a rotation, for instance, by an angle theta around the z-axis, okay, I can show to you that this operator coincides with e to the minus I, the theta, the angle, divided by h bar, the angular momentum operator. Okay, so this is very, very interesting, similar obviously to the momentum case, but slightly more complicated to derive. Okay, let's try to see how you derive these things. Okay, so derivation. First of all, the definition. The definition is that P of this rotation applied to a function psi of x is equal to the function calculated at the rotated back point. Okay, this is the point which has been rotated back in the opposite direction with the inverse transformation. Okay, now I consider r theta z to the minus 1 of x. Okay, what it is, I have to take the rotation matrix and invert, right? Invert means take the transpose. So I have cos theta, 1, 0, 0, 0, 0. If I want the inverse, I just transpose the one I wrote for you before, and I get this. Okay, so please go and look, but I will show it to you. You see that here there was minus sign in the first row and sign in the second, and here I have exactly the transpose of it. Okay, very good. Now this has to be applied to the vector x, which is 3 component, x, y, and z. Okay, so if I do this matrix multiplication, I get 3 objects. One is x cos theta plus y sine theta for the first component. And then I get minus x sine theta plus y cos theta. And the third component is untouched. Is it clear what I have done here? I have done my matrix times product times a vector. Okay. Now, in principle, this is what? This is x plus some delta x. This is y plus some delta y. And this is just z. Okay. This delta x, what is it? Okay. Delta x, I read it, is equal to x cos theta plus y sine theta minus x. Okay, by definition, I write x plus something. And the same for y. You might ask, why do you want to write x plus something if this something is just obtained by just subtracting x? For a reason. Just wait for a second, I will explain to you why. Okay, so this is equal to the y cos theta minus x sine theta minus y. The reason is that I now want theta small, in fact, infinitesimal. Okay, if theta is small, okay, Now you see that I can apply the rule that cos theta, I'll tell you here, cos theta is roughly equal to 1 minus theta square over 2, okay? And sine theta is roughly equal to theta plus, okay? Now you see immediately that this implies that delta x is equal to, you see the cosine being 1 up to order theta square implies that up to order theta square, this and this cancel. And the only thing that survives is simply, okay, y times theta plus higher order. Is it clear? The theta comes from here, okay, and from here. Good. Let's do the delta y.
Professor,
Yes, please.
The cosine you only take until order 1, not theta square. Is it true or?
Cosine is 1. And if I want to get the next order, I get theta square. So up to linear order is 1. That's the point. I want to keep only up to order theta. Sorry, up to theta. Okay? So I forget about theta square. You see, I stop here at theta. There is no, in the dots, there are theta square, theta cube, all higher terms. Okay? I forget them. And for delta y, same thing. You look at the formula here, and you see that the cosine and the -1 cancel, so I get simply minus x times theta plus dots. Okay, is it clear? Very good. Okay, if you are happy with that, let's look at our formula. The formula is so far the following. This P is equal to the psi at this point. And now the point is calculated in this way. Okay, good. Let's try to rewrite the expression. So I have the P of r and theta z applied to the function psi of x is equal to psi of the function x plus delta x, y plus delta y, and z. Okay, this is my first step. Okay, and then I say that this is equal to, since delta x and delta y are now assumed to be small, okay, of order theta, so I now say that this is equal to psi of x plus delta x times the derivative of psi with respect to x plus delta y times the derivative of psi with respect to y plus other terms of higher order in the Taylor expansion. Since I am already neglecting the higher order in the delta x, there is no point in keeping them here, okay? So my expansion here is stopped at first order.
Professor,
Yes.
shouldn't you also write psi y or not?
What?
So you wrote psi x. Initially, psi is the function of x, y, and z, but you
Sorry.
wrote only
Yes.
psi.
Yes, this is a vector. So x and y and z. Yes. You catch the problem with my notation. Let me write it explicitly. X, y, z. Okay? Good. So here, x is the vector x, y, and z. All right? Very good. Now, you see that delta x is equal to here, y theta. So this is y times theta, and this is minus x times theta. So let's do the algebra. So this is equal to psi at the same point, x, y, z. Then I have plus theta, y, the derivative with respect to x, minus x, the derivative with respect to y.
Professor,
Plus, yes.
I don't get the y theta and minus x theta.
Oh, yes. Okay. Yeah, here. I calculated already for you to lowest order what delta x and delta y are as a function of the small theta. And they are delta x, you see, is y theta, and delta y is minus x theta. Is it clear now?
Yeah, it is.
Okay, good. Very good. So I substitute and I get this expression. And now, if you remember, LZ was what? Was x py minus y px, where these are operators, right? So this is equal to minus I h bar, x, the derivative with respect to y, minus y, the derivative with respect to x, right? In real space representation. And now you see that what you have here is closely related to LZ, right? And in fact, you can verify in one line of algebra that this is equal to psi at the same point minus I theta over h bar LZ applied to the function psi, okay? Plus higher order terms, okay? Now, I have proven to you that the goal was to show this, right? It was more ambitious. It was to show that the operator is in fact the exponential of the angular momentum. I have proven to you that this first term is right, okay? But only the first term, okay? I just proved to you this, if you look. Is it clear? There it is, okay? The point is how to explain that all terms are indeed right. So all these dots here are indeed correctly reproduced. In order to do that, I would need to do very, very annoying algebra. First of all, I cannot stop here to lowest theta. Second, I have to account for Taylor expansion to all orders, okay? So it's a very, very boring exercise if you try to go beyond first order. But luckily enough, there is a more general route, okay? But this general route, as usual, requires a little bit more of mathematics. So we have to do a little bit of generalization before we can actually do this, okay? It's not difficult. The generalities are useful, okay? So generalities. First of all, we said the operator associated to a transformation acts by just giving me a function at the point that is somehow transformed back. Okay, this is my definition of P of t. Very good. Now, clearly, there are two things. This P of t are unitary operators. Okay, in other words, they conserve the scalar product. Unitary means that they conserve the scalar product. Okay, so if I calculate the P of t of some function psi1 and the p of t of some function of psi2, okay? I want to prove to you that this is exactly equal to the scalar product of psi1 and psi2. How to prove it? Proof. Very simple. I just calculate the integral over x, okay, of the object on the left, which is the psi1 star, but calculated at t to the minus 1 of x. And then I have psi2 calculated at t to the minus 1 of x. Is it clear? This is the left hand side. Okay? Now notice that here I am integrating over x, but the integration variable is t to the minus 1 of x. How about changing variable, okay, and defining y equal to t to the minus 1 of x, okay? So this becomes y, and this becomes y. Do you know what is the Jacobian that I have to use in order to change variables in this multidimensional integral? Well, is the determinant, the Jacobian is the determinant of the transformation t to the minus 1, or better, the modulus of the determinant. How much is the, so this is the Jacobian that I have to use. How much is the modulus of the determinant of a space transformation? +1, right? Remember, both for translation, for rotations, the determinant of the transformation is always 1. Is it clear? At this point, I can just transform this object into an integral over y of psi1 star of y, psi2 of y, okay, which is equal to the scalar product of psi1, psi2, okay? So the transformation indeed conserves the scalar product, okay, of the functions. So it is what people call a unitary transformation. In other words, if I bring, for instance, this thing to the right-hand side of the product, okay, I do have that pt of psi1, pt of psi2 is equal to psi1, pt dagger, pt psi2, okay? And this thing is equal to psi1, psi2 for all psi1 and psi2, okay? This implies that for unitary transformation, the p dagger p is equal to the identity, okay? This is a very important definition that unitary operators satisfy. Very, very similar to rotation transpose, rotation equal to the identity for rotations, okay? Remember that I told you that the rotations are orthogonal transformation for which the inverse is equal to the transpose. Well, that's exactly the reason why. And this implies, in turn, that the inverse of a unitary transformation is equal to the dagger, okay? For unitaries. Is it clear? This is an important fact. So unitary transformations are similar to rotations, but in the Hilbert space. So their inverse are simply the dagger of them. Okay. Now, I want to conclude my proof, okay? Remember that I proved that by the way, they form a group. Okay, so the first property is that they are unitary. The second property, they form a group. Okay, what is the group property? The group property is very simple. P of a certain transformation T2 following P of a transformation T1. Okay, try to verify. Please do it yourself this time. Don't let me do it. Very, very simple. But verify that this is equal to P of T1, T2, apply obviously to the function. Okay, so you have to verify, you apply the left-hand side to a function, the right-hand side to a function, okay, and you verify that the result is the same. Okay, notice the order in which these two things appear and the order in which these two things appear. Okay, try to do it, because there is an inverse transformation that is always involved. Okay, and remember that the inverse transformation, when you do apply them repeatedly, is the inverse of the reversed. Okay, so try to do a little bit of thinking about this. Good. These are properties of unitary operators. Now, this PT, oh, sorry, this PT associated, sorry, to the rotation, okay, are in fact unitary operators. So let's suppose that I have a rotation by some angle theta plus some small angle epsilon around Z, okay? Now, I told you that they are unitary and they form a group. So that is exactly equal to the transformation applied to an infinitesimal rotation, okay, following the transformation applied to the theta rotation. Okay, is it clear? Because the composition of simply r of theta plus epsilon z is equal to r of theta and r of epsilon. Okay, is it clear? Then you apply the rule that I have explained to you, and you immediately deduce that it must be this one. Now this, I know what it is, because it's an infinitesimal rotation, okay? So if you look at our expression for infinitesimal rotations, I know that the result is this, okay? So let's try to use this to write a differential equation. So the goal is to write a differential equation, which I can then solve. Okay, it's a very neat trick. Okay, so I do write this as 1 minus epsilon, there is an I, over h bar, the angular momentum operator plus dots. I know it only up to first order. And then I apply it to P of r theta and z. Okay, very good. Now so these objects are order epsilon square. Okay, now I calculate the derivative with respect to the parameter theta of this P of r theta and z. How do I do it? I do as a limit epsilon going to 0 of the P of r theta plus epsilon minus P of r theta divided by epsilon. Is it clear? This is the definition somehow of the derivative of this operator with respect to theta. I just take the rotation plus a small epsilon, I subtract the rotation and I divide by epsilon. Is it clear? Is the definition of derivative by limit of the incremental ratio. Okay? Is it clear to everybody?
Yes.
Okay, good. Now, if you take this expression here, you see, I have P of R theta plus epsilon, which is this. Okay? And then I subtract the P of R and theta, which is the 1. Okay? If you do the algebra, you will see that the result of this subtraction, okay, is minus I epsilon LZ over H bar plus the order epsilon square term, which I didn't indicate, divided by, times P over theta. Okay, the 1, in other words, is cancelled. That's the crucial point. This 1 is cancelled when I take I subtract the P over R and theta. Okay, so the 1 cancels, and then I divide by epsilon, and the result of this thing is equal to minus I over H bar LZ plus order epsilon applied to P of R and theta Z. Okay, now I have to take the limit. Sorry, this is a mistake. I have to take the limit, epsilon going to 0. Now, can you do the limit now? Obviously, yes. For epsilon going to 0, this object totally disappears. So the result of the limit is equal to minus I LZ over H bar P of R theta and Z. Summarizing, I have proven to you that the derivative with respect to theta of P of R and theta Z coincides with minus I LZ over H bar, the same operator. Now, can you tell me a solution of this object, of this differential equation? I propose to you a solution, and then we verify.
E
The
power
solution is
P.
E to the power minus I
Minus-
LZ.
E to the minus I theta LZ over H bar. If you take a derivative with respect to theta, you bring down precisely this factor, leaving the same thing. By the way, this is a solution such that if I take theta equal to 0, I obtain that the operator, so the operator with the rotation theta equals 0 is obviously equal to the identity, right? You do not rotate. So, okay. So I have proven to you that indeed, not only to first order, but to all orders, okay, the rotation operator is associated in the Hilbert space to the exponential of the angular momentum, okay? And that's true, in fact, for any rotation, okay? Although it's, I mean, so if I have a rotation by an angle theta around any axis n, then the P of, say, R theta around n is equal to e to the minus I theta over H bar n dot the angular momentum operator. Okay, so that is a very important conclusion okay, which I showed only for RZ, but accepted as a general fact. So the operators that act on the Hilbert space corresponding to rotations in space are the exponential of the angular momentum. Pretty much similar to what the translation do with the momentum. Now, unfortunately, I do have still a few things to tell you, which I would like to do them today. Otherwise, we would leave things to do. So I want to discuss now, in the last 10, 15 minutes, sorry, I've described to you space transformation and how they act on function. Now I want to describe symmetry properties of the Hamiltonian. So far, I didn't talk about the Hamiltonian at all. I talked about transformation in space and operators that act this transformation on the functions. No mention of the Hamiltonian was made, okay? Now, if I have some Hamiltonian expressed in the variable x, I can do a transformation of the x into x prime, okay, which is this t of x, a transformation, translation, rotation, whatever. And I would like to know how this Hamiltonian is connected to the Hamiltonian in the new variable, okay? What is the relationship? Now, if the two are the same, then you say that T is a symmetry of the Hamiltonian, okay? So if the Hamiltonian expressed into two variables are the same, then T is a symmetry. Let me give you examples, otherwise it will be a bit obscure, okay? Now, suppose that I have, for instance, that T is a translation, so T of A, okay? So equal to X plus A. Now, suppose that I am in free space and my Hamiltonian is just P squared over 2M. No potential, okay? So there is no potential. Then obviously, since the derivative, okay, so this is x prime. Now, since the derivative with respect to x prime is equal to the derivative with respect to x, I'm simply translating the x. It's obvious that the momentum in the new variable, okay, is equal to the momentum in the old variables, okay, because the derivatives are the momenta. And therefore, in the new variables, so if this was the Hamiltonian in the x variable, in the new variables, I do have that, sorry, that the Hamiltonian is equal to P prime, sorry, P prime square over 2M, okay? So the Hamiltonian actually coincide in the new and old variables, okay? Let me give you a less trivial example, okay? Suppose that I have, say, a rotation, okay? Rotation R by any angle, then I know that x prime is expressed as rotation applied to the vector x, right? An orthogonal matrix. Now you can verify very easily that the derivatives, okay, so d in the x prime, d in the y prime, and d in the z prime are related to the all derivatives precisely with the same matrix x. Try to verify. Okay. In other words, if I have x and x prime connected by a rotation matrix R, then P prime is also equal to the rotation matrix applied to the vector P. Okay? It's a very interesting thing. So the momenta are simply rotated themselves as the coordinate. Therefore, P square, which is the square of the momentum, okay, you realize that it must be equal to P prime square, right? Because if you rotate a vector, the length square of the vector doesn't change, okay? You can prove it more precisely, but it is pretty obvious that since this is, okay? So the kinetic energies are always insensitive to rotations and insensitive to translations, okay? So let me just do as an example the hydrogen atom Hamiltonian, okay? Here it is, P square over twice mu minus Z E square over X, okay? Very good. Now I do a rotation, R. So X goes into X prime equal to R times X, right? The length of X is equal to the length of X prime, right? So in the new variables, and also I just proved to you that P square is equal to P prime square, okay? So as a consequence, what I have is that the Hamiltonian in the new variables, okay, which is P prime square over twice the mass minus Z E square over X prime is totally equivalent to P square over twice the mass minus Z E square over X, okay? And this is the Hamiltonian in the old variables. Is it clear? Okay. So this is
Yes.
what I mean when I say that rotation is a symmetry of this Hamiltonian. Okay. So rotation is a symmetry of this H. Now let me just show to you a case where the rotation would not be a symmetry. So let's consider this other example. I am in 2D and the potential V of X and Y is equal to the following thing. I don't draw it. I'm sorry, I don't write it. Or, I mean, is the following thing. So suppose that I am in 2 dimensions. The potential is an infinite square well, but now in 2D. So it is 0 inside, in the yellow part, and is equal to infinity outside here. Okay? So here is infinity, and here is 0. Okay? So it's a 2-dimensional square well. Now, if you rotate, okay, by an angle theta, is V of X prime, Y prime equal to V of X and Y?
No.
No. Okay, so rotations is not a good symmetry for this problem. Unless you rotate by theta equal to, well, pi, certainly. If this is a square, also pi over 2 is good. Minus pi over 2 is good, okay? So only some rotations are symmetries. Okay, is it clear? Is it clear? So generally speaking,
Yes.
what transformation leave the Hamiltonian invariant depends on the Hamiltonian. Okay, Some Hamiltonians are fully rotational symmetric, some are only partially rotational symmetric. By the way, the hydrogen atom is not, okay, translational invariant, because if you send x into x plus a, the potential is different, okay? Although, if you take the nucleus and the atom and the electron together, both of them are symmetric. In other words, if you consider the two-particle problem, then that is translational invariant, okay? But not the reduced problem, okay? And we know that, in fact, the two-particle problem has, yes, please.
I didn't get why just some rotations are symmetries.
Why some rotations only?
Yes.
Well, you see very clearly that, if I do x prime and y prime, which is a rotation by, say, 45 degrees, the potential is not the same, okay?
Yes.
So take this point here. Rotate by 45 degrees, it ends here, okay? And now you see clearly that here the potential is equal to infinity and here is 0. So
But
V of
with
x prime, huh?
But with rotation of pi or pi over 2, it's
Well, rotation of pi over 2, yes, because then this object, if you rotate by pi over 2, ends up in here, right? And therefore it is still the same value. For pi also it's clear, it ends up here. Minus pi over 2 ends up here, okay? But if you rotate by pi over 4, ends up outside, and therefore it's not the same, okay? Okay, is it clear? Good, let me close this story about examples of what are symmetries and what are not, because we are kind of late. I just want to highlight to you the important theorem that remains to be, okay, explained. The theorem is the following. I can define a group G of H, which is the group given by all space symmetries of the Hamiltonian H, okay? How big is this group depends on the Hamiltonian. The Hamiltonian could be invariant under all rotations, under some rotations only, under all translations, under some translations only, like in a lattice Hamiltonian. Remember, the crystals do not admit all translations, but only some discrete translations, okay? So how big is this space of a group of transformations that leave the Hamiltonian invariant depends on H, okay? So this is called the invariant group, invariance group of H. Notice I say group. Why group? Well, because if I have a certain transformation, okay, by the way, these are transformation T. If T1 leaves the Hamiltonian invariant and T2 leave the Hamiltonian invariant, so both belong to the group of the symmetries of the Hamiltonian, then it's obvious that T1 times T2 also belongs to the group of the Hamiltonian, okay? This is kind of a simple thing to realize. So it is indeed a group. Very good. So now comes the very, very important theorem. Take G of H, take the set of all T of all transformation, these are transformation, such that h in the x prime is equal to h in the x. So the Hamiltonian is invariant in the old and in the new variables. Remember, x prime is equal to the transformation of x. Okay, very good. To each t, I can associate a pt. Okay, remember, pt of psi of x is equal to psi of t to the minus 1 of x. Okay, you remember the transformation now on the functions. So this is in the Hilbert space. Notice the difference. T acts on the space. Okay, this acts on the space x, and this pt acts on the function. Okay, very good. Now, theorem. All the pt such that t belongs to the symmetry group of the Hamiltonian. Okay. Theorem. Oops. Form a group of unitary operators. First statement. This is kind of obvious. The fact that they form a group, since, I mean, they tend to form groups in general, but in particular, I have told you that the symmetries of the Hamiltonian form themselves a group. So, I mean, it's a very simple conclusion. And the fact that they are unitary, I showed to you before. Okay. So the only important part of this theorem is part 2, which tells you that pt commutes with h, with the Hamiltonian, for all t belonging to the symmetry group of the Hamiltonian. Okay? So the commutator is 0. This is the important part of this theorem. The fact that the corresponding pt commutes with h. Okay? How to prove this is simple. Proof. Let's consider a function, psi of x, okay? And I act on this function first with h, and then with pt, okay? In this order. Now, at this point, h is h in the x variables, okay? I denote the variables by which the Hamiltonian, over which the Hamiltonian is written with this little index a x here. Okay, so this object here is equal to pt acting on a function. What function is it? Is a function phi of x. Guess what it is? Phi of x is the Hamiltonian acting on the psi of x. Okay, it's as simple as that. The Hamiltonian in the x variable acting on the psi is a function. This is what I should calculate, the action of pt on this function, right? But according to my definition, this is equal to the function calculated at t to the minus 1 of x. You remember why, right? Is the definition of pt. Remember that pt does precisely that. Sorry, it's a bit further away. Too far away. Where is it? Oh, so far away. It's almost forgotten. Here. Okay. P acts in this way that we have seen several times. Okay. Very good. Now, I go back. Where is it? Here. No, was here. Was also here. Sorry. No need to go so far back. Okay. Very good. Now, so I use this here. Okay, and I find this. So this is the function calculated with the variables t to the minus 1 of x, which means, read here, that this is the Hamiltonian calculated with variables t to the minus 1 of x, applied to psi calculated to at t to the minus 1 of x. Okay, by just looking at this definition of phi, I conclude. Okay, but this is equal to the Hamiltonian in the variable t to the minus 1 of x times, you see here, this is psi of t to the minus 1 of x. What is it? According to my definition, is pt acting on psi of x. Okay? But the t are belonging to the invariant group of the Hamiltonian. So this object is in fact coincident with the Hamiltonian at x. Okay? And therefore, I have concluded that this is equal to the Hamiltonian acting after pt on the function psi of x. Okay? Notice the order is now reversed. Here I have pt applied after the Hamiltonian. Here I have the Hamiltonian applied after pt. Is it clear? Very, very simple two-line exercise. Okay? Please.
How you get a Hamiltonian of t minus 1 x to equal to Hamiltonian of x?
This.
Yeah, the before the last equality.
This one.
Uh-huh.
Remember, T belongs to the symmetry group of the Hamiltonian. This means the following thing. So T belongs to the GH. This means that if I take T of x and I take the Hamiltonian in x and the Hamiltonian in T of x, which is, by the way, x prime, they are exactly the same. You might say, hey, wait, you are tricking me. Here I have t to the minus 1. Correct. But if t belongs to the symmetry group, then also the inverse belongs to the symmetry group of the Hamiltonian, right? And therefore, I can consider the same story for t to the minus 1. Okay? So in fact, it's not very different from t of x. Is it clear?
Yes, thank you.
Okay, so this is the equality that is behind this last step. Okay? Very good. Now, this theorem tells you that if I have a symmetry group of transformation, which leaves the Hamiltonian invariant, the corresponding PT commute with the Hamiltonian. Okay? This is a very, very remarkable conclusion of our story. Now, you remember that when things commute with the Hamiltonian, I can diagonalize them simultaneously. Okay? So this is indeed now the crucial theoretical basis over the fact that I can simultaneously diagonalize my Hamiltonian with a certain symmetry transformation, all in a moment. Okay, you remember, for instance, that we already used this. Oh, by the way, yes, where did we use it? One, hydrogen atom. Okay, remember, I told you that all rotations, so T equal rotations, are symmetry, belong to the symmetry group of the Hamiltonian. Okay, we saw it a while ago, which means that all P associated to rotations, in fact, commute with the Hamiltonian. Okay, but the P associated to rotations are exponential of minus I theta, any axis, the angular momentum, and this must commute with the hydrogen atom Hamiltonian. Okay, since theta is arbitrary, okay, you realize that, take derivative and do a little bit of algebra, that this implies that any component of the angular momentum, okay, must commute with the Hamiltonian. Okay, and we know that indeed the Hamiltonian commutes with Lx, Ly, and Lz. It commutes with L square. It commutes with Lz. Okay, so I can take three operators. One is the Hamiltonian, the other one is L square, the other one is Lz. All these three operators commute among each other. Okay, you cannot extend it anymore. You cannot include Ly or Lx because Ly and Lx do not commute with Lz, remember? Okay, but these three commutes. So I can find common eigenstates of the three. And in fact, if you remember the functions, which are radial function, radial function times spherical harmonics, these are eigenfunction of L square and Lz, and the combination of this radial and spherical harmonics is an eigenfunction of H as well. Okay, so I've constructed, by using the symmetry and by using essentially the spherical harmonics, common eigenfunctions to this set of three operators that commute among each other. So I have used symmetry heavily. Okay, if you remember our exercise with even and odd functions, or for instance, even the harmonic oscillator, the inversion, so the parity, what is called the parity. Parity is x into minus x in one dimension. It's essentially the inversion. Okay. Now, do you know how the operator acting on associated to inversion acts? P of psi of x is equal to psi of the inverse of x. What is it? It's minus x, right? Now, do you know how to construct eigenfunction of this object here? If I ask you, please tell me eigenfunctions of this operator that sends a function to the function in minus x. Do you know what they are? Think of an even function. So a function such that psi of minus x is equal to psi of x. What happens? It happens that pi of the psi even of x is equal to psi even of minus x, which is also equal to psi even of x. And so immediately you realize that this object here is an eigenfunction of the parity operator with eigenvalue +1. Okay? Now think of an odd function. So a function such that psi of minus x is equal to minus psi odd of x. And then look at what happens to this function as I apply the parity operator to it. According to my definition, is psi odd of minus x, but this is equal to minus psi odd of x. And therefore, we immediately see that this is an eigenfunction with eigenvalue -1. Okay? So even and odd functions are eigenfunctions of the parity operator with eigenvalue +1 and -1. Since I take, for instance, v of x equal to 1/2 m omega square x square, or any, in fact, even potential, so v of minus x is equal to v of x. Therefore, the Hamiltonian in the transform variables, so in the minus x variables, and the Hamiltonian in the x variable are absolutely identical. So you say that parity is, or inversion is, a symmetry. Okay? So according to our theorem, then PT, so this inversion symmetry, parity operator, commutes with the Hamiltonian. Okay? So I can find common eigenfunctions of H and of this, which means that the eigenfunctions psi, eigenfunctions of H are either even or odd. Okay, they must have a definite symmetry. They must be eigenstates of the parity operator themselves. Okay, they cannot be hybrid. Okay, either they're even or they are odd. Is it clear?
Yes.
So this is a consequence of our general theorem. So many consequences follow when you consider a good symmetry of the Hamiltonian. You are immediately guaranteed that the corresponding P operator, the corresponding operator on the functions, in fact, commutes with the Hamiltonian. And I can diagonalize it simultaneously. For instance, if I'm doing things numerically, I know that I can reduce myself to blocks. Okay, I don't need to diagonalize the full matrix. I can just act in blocks because the two objects commute with each other. Okay, so please read the remaining part of the lecture notes. There is a small story about how to use symmetry to conclude that certain matrix element are zero. Okay, this is useful when you do perturbation theory as well. They are called selection rules. So I leave it to your study. So study 10.5. The selection rules associated to parity. So parity selection rules. Very, very simple. Try to do it yourself, okay? We are pretty late now. And this is something that you will probably encounter again in doing perturbation theory, but please try to do it yourself.
I wanted to ask a quick question, Professor.
Sure. Yes.
Yes. This is about the Hamiltonian symmetry.
Yeah.
Is it if we for example, in solid state physics, these block functions, which are indeed um, sort of symmetric, or will I say just periodic? Is it okay to look at?
It is connected.
This
So, solid state.
yeah,
I have a
so-called
crystal.
Floquet.
No, that
Floquet.
Floquet is for time. Floquet is for time. Forget it. Okay. Yes. I mean, it's very similar to block is very similar to Floquet in space. However, in solid state, I have a crystal, which means that not all A are allowed. Okay. I cannot translate by half a lattice spacing, for instance. If I have this crystal, okay, I can translate by this A, but not by this. Okay. In other words, if I have some potential, okay, V of X, if I translate by exactly the lattice spacing, V of X plus A is equal to V of X. If I choose A prime, which is not a direct lattice vector, then it's different, right? So you see immediately that some discrete translations, so discrete translations, so the lattice translations are symmetries of H, okay? Now, it means that I can diagonalize simultaneously P of these discrete translations with the Hamiltonian, okay? And they are zero. And in fact, block wave functions, okay? The block wave function are classified by a certain k vector k, and they do obey the fact that if I translate by a lattice spacing A, what I obtain is e to the I k dot A times the psi of x, okay? Because you remember that the psi of x can be written as a plane wave part times a periodic part, okay? So the periodic part, if you change x into x plus a, doesn't change. For the plane wave part, you get this factor here, okay? These are indeed somehow the Eigen functions, okay, of the PTA, okay? The possible eigenvalue of the translation by a unit vector A, sorry, not a unit vector, a vector A are the block functions. So everything is absolutely consistent with what we just saw, okay? Simply,
Yes.
you have to look at the at this object in the right perspective, okay?
Yes. Yes.
Good.
But I see no reason why you should why you said that we should one should forget Floquet Hamiltonian, even though it's in time. Is it wrong to assume that there is no symmetry in time or something?
I mean, very often in time, there is total homogeneity. In other words, H doesn't depend on T.
Yes.
Therefore, I mean, you know that you can do any translation in time. And in fact, the corresponding unitary evolution is this. Okay.
Yes.
If I take any state, psi, so if I translate by tau, by time tau, a state C of t, I get psi of t plus tau. Okay. For any tau. Okay. So I can translate by any tau. Okay, you see. On the contrary, there are situations where, so the Floquet case applies in very specific situations. Suppose that I have a Hamiltonian that depends on time, but in a periodic fashion. So h of t plus tau is equal to h of t. Okay? Then I say that the Hamiltonian depends on time, but tau is a period. Okay? Then you can prove a few things, okay, about the evolution operator, but never mind, okay?
Okay.
Okay, there is a so-called Floquet theorem. But this is not the right place to actually do it because we are late and it would take a full lecture, okay?
Yes, thank
So
you.
it applies to situations where the Hamiltonian, Floquet theory, where the Hamiltonian is time periodic.
Oh, okay.
Okay, time periodic h. Okay, in most of our cases, the Hamiltonian is time independent. Obviously, you could think of time periodic electric field, for instance, and at that point, the Hamiltonian, including the electric field, should be time periodic. So there are physical situations where Floquet theory is important, obviously, but we completely neglect it.
Professor,
Please.
Are we not going to discuss Euler rotations?
Not much. Euler angles, you mean Euler angles?
The one in Sakura.
We will stay very elementary on that, okay? So usually we do rotations about a single axis, like Z or things like this. A general rotation, okay, we see, yeah, let me just tell you one important thing, and then we stop. I told you that if I have a rotation by an angle theta around an axis n, okay, then I have that e to the minus I theta over h bar n dot L is the operator associated to this rotation, okay? Now, one thing that you should not think is that this is equal to e to the minus I theta n along x Lx times over h bar e to the minus I theta and y Ly times e to the minus I theta over h and z and z. Okay? In other words, it's not good to think of this as three components and then split the objects in the exponential, because remember that these three objects do not commute, so you cannot split exponential of angular momenta. It is because of that that you need to parameterize the rotation with Euler angles in order to be able to express a single rotation by an angle theta around some axis n as a product of three elementary rotations with appropriate angles, which are called the Euler angles around the axis, say Z, Y, or whatever, okay? So in order to rewrite the full rotation in terms of 3 elementary rotation around the axis, you need the Euler angles. But this is somehow a more complicated subject. It's important in some applications, but for us, it's not crucial. Just remember that the story about rotations is more complicated than the story about translation, because for translations, so notice, for translations, I could split. If I have e to the minus I a dot p over h bar, this is equal. So while this is different, this is equal to e to the minus I ax over h bar px, e to the minus I ay over h bar py, e to the minus I az over h bar pz. In other words, for translations, if I have to translate by a, I can just do it separate. First, a translation by certain ax, then a translation by ay, and then a translation by az. Okay, I can do the three translations in the order I want. I obtain the net effect. Okay, for rotations that's not true. Okay, so you shouldn't think that
Professor,
you just rotate around the x-axis, y, and z with the simple rule that I gave here. That's not true. You have to use Euler angles, please.
I think this is related to the BCH equation that you didn't mention. The
What? The
BCH equation. The e to the power of a times plus b is equal to e to the power of a e to the power of b times e to the power of commutator of b and a.
Well, but that's only it's not a general equation.
Yeah.
It only holds if the commutator is a C number. In general, the only simple statement is that the exponential of operators that do not commute cannot be split. Okay? If in some cases you can write formulas, okay, to capture this. And then, by the way, in one of the exercises on the harmonic oscillator, we use this Baker-Campbell-Hausdorff formula. I think it's in an exercise in the harmonic oscillator shifting of the harmonic oscillator. So the I mean it was used there, but I mean it's a more complicated topic again, and I prefer to skip it. But certainly operators that do not commute cannot be split. Okay. While the three components of the momentum commute, and so you can split them, okay? So physically means that translations can be done in any order, doesn't matter. Rotations matter. As you know very well, if I first rotate around Z and then around X, I get a different results than doing the reverse rotation, right? You can do it with your book. Try to rotate in the two orders, and you will see that the result is absolutely different, depending crucially on the order of the rotation. So, I mean, the thing behind is that exponentials of non-commuting operators, like the angular momentum, are not split in general. Okay, so it's a more complicated subject. Forget it. Okay, don't be worried about it. It will not be in the exam. It's a more advanced topic. Okay, just be aware of it, however. Okay, so Euler angles are useful for more complicated applications, but not for our purposes. Okay, I think we should stop here. It's half an hour past the time. You have to go and eat something. Okay.
Yes.
Good.
Thank you.
So yes, next time there will be Professor Fazio starting the lecture, okay? So anything you would need, please do not hesitate. Send an email, we'll try to do things, okay?
Yes, Professor.
Sure.
Yeah,
Bye.
this is just, oh, no, this is outside the quantum. Like, maybe if someone needs a reference from you, if he's applying, please, you can provide one. It is just I'm asking.
What? The reference, a letter? You mean a reference letter?
Like a recommendation to a PhD. If I
Oh,
need
yes.
one.
The ideal thing is, however, make sure that, first of all, one, I have already seen you in some exam. Okay, so don't ask me a letter before, say, the final, because at least I must know how you roughly performed in order to state something. Otherwise, it's an empty letter. And the second thing is ask the professor where you performed better in the finals. Okay, because it's usually, I mean, if you get a C or you get an A, okay, the letter is different, okay, inevitably. So try to fish out a professor for which you do the best in the exams and ask them to write the letter, okay?
Okay,
This I
thank
would
you.
say
Yeah.
my suggestion. But
Okay.
yes, generally speaking, yes, why not? Okay?
Okay, thank you.
Good. Stay well. Ciao. Bye-bye.
Bye.
Bye. Ciao, ciao.